Good morning, Physics 30. I hope you guys are all doing well today. So, welcome to our lesson on Half-Life. So, what this lesson here is going to be about is about essentially the time of radioactive decay. Now, this is really useful in archaeology and geology for dating the age of various rocks and artifacts. So, carbon-14 is a radioactive compound that is found in living things. So, by doing carbon dating, you can get a range of when this particular artifact, when it may have come from. Now, it's not going to be 100% accurate, but you can at least get a ballpark of where that artifact came from. And you can also get to how do we know the age of the planet Earth? Well, we know that through radioactive decay of some of the nuclear elements. So it's pretty cool. So this is a very relevant area of science outside of physics as well. So it's really cool, actually. So, ladies and gentlemen, this is not a painfully difficult set of equations, but there's a couple tricky bits which I will highlight to your attention here. So our definition of half-life, it is the time required for 1/2 of the radioactive nuclei to spontaneously decay. So when we say spontaneously decay, that radioactive element is just going to sit there and decay on its own. All right? Now, there's a lot of other things that have half-lives as well. Like, for example, in biology, enzymes have a half-life. So it depends on what enzyme, but an enzyme will only be able to stay folded and do its job for a certain period of time before it breaks down and has to be, its amino acids chopped up and recycled. So same idea. So the enzymes will have a half-life. So a certain time for half of them to have broken down. All right. And viruses, for example, COVID, also has a half-life. So what that would mean is how long does this virus survive on the surface of an object before half of it is gone? So don't quote me on this one. I think it's about 2 weeks, but don't quote me on it. Okay. It depends on a whole bunch of other stuff. Okay. So with this, ladies and gentlemen, the half-life as far as radioactive nuclei, it's specific to the type of radioactive material. So different radioactive elements are going to have unique half-lives. Some of them are going to have half-lives in the forms of thousands of years. Some of them may have half-lives in hundreds of years. And some of those that are used in nuclear medicine may have half-lives in the form of hours. So it just depends on that element. So the number of nuclei in the original isotope can be calculated after a certain amount of time, can be used with this equation. So this guy is on your data sheet, and you can find that equation right here under atomic physics. Okay, so right there, there's your equation. And I'm going to scroll down so you guys can read this through that video tab there. Okay, so N is the amount of radioactive material after a given amount of time. So however much is left. And O is the original amount of the sample prior to decay starting. Little n is the number of half-lives that have occurred over a given period of time. Okay, so we'll talk about that in a bit more detail after our next equation. So this guy, ladies and gentlemen, is not on your data sheet. So my advice is pause the video right now and write this equation on your data sheet right now so you have it. Pause. We're back. Okay. So now that you have this written on your data sheet, T is the given time period. So however many years it has passed, 20 years, 5,000 years, whatever the question's saying for how much time has passed, in total. T half is the half-life of an element. So let's talk about number of half-lives a bit. So I'm going to use some pretty simplified numbers just to give an idea of how it works. So for the number of half-lives, so let's look at this equation. Let's say for a particular radioactive element, we'll say 2 years. Let's say the half-life, okay, so the T half is 2 years. So if you have a 500 gram sample, 2 years later, half of it is going to have decayed. So that means you're going to have 250 grams left. Okay, well, how many half-lives is that? Well, if a half-life is 2 years, how many half-lives? Let's say 6 years has passed. So if the time that has passed is 6 years, well, if it takes, how many half-lives is this? Well, the number of half-lives, 2 years, divided by 6 years, well, that means 3 half-lives is going to have passed. Okay, so I wrote it down backwards. I did. It's Monday, and it actually is Monday this time. There we go. That's better. So with this, ladies and gentlemen, if you have any questions with half-lives and exactly how they work, sign up on Google Meet, and we can go from there. All right. So, ladies and gentlemen, this bit here is really, really important with half-lives. So, the amount of the radioactive material can be expressed in different units, and a ton of different units. So, for example, you could have it in mass, number of atoms, percent, decays per second, whatever, a measure of activity. So, tons of different units can be used to measure this. So, but as long as NO and N are in the same unit, then you're fine. Okay, so this formula can handle any type of units so long as N and NO are the same units. So the big thing here with this one is don't let the units distract you from the actual question. Okay? So don't let the units distract you from the actual question. Sounds good, guys? Cool beans. All right, so let's look at a couple graphs and see what we can do with those. Now, what you will notice here is that this is an exponential graph, okay, which makes sense, okay, because if every time we go through, half is going to be decaying, you're going to wind up with this logarithmic style graph. All right, so let's look at this graph. We have activity counts per second, and we have time. All right, so this on your Y here, we have some measure of N, okay? So some measure of the amount of radioactive material. Now this guy here, that is the original amount, okay? So that's where we're starting up there on our graph. And what does the original amount mean? Come on, guys. NO. There you go. So that's where NO is on this graph here. This is some measure of N. Well, if we want to figure out, well, what is the half-life of this? Well, let's make our lives easy and let's give ourselves some space to work on the graph. I am not going to be starting at 80 and 40 as half of it being gone, because look at the difference where the line is at like 80 and 40. It's tiny on that x-axis. So it's going to be hard to work with. I'm going to work with 60 and 30 because they're going to be spread out more on the graph and it's going to be easier for me to read, and I'm going to get the same answer in the end. So here is 60 and 30 is right there on the graph. Okay, so because 60 and 30, well, 30 is half of 60, then half of the material is lost. So from here to here is going to be 1 half-life. Okay, so you can be any number. I just picked these because they're going to be far enough on the y and it's not, or on the x, excuse me, it's not going to be a pain to read. So I'm going to take your ruler and I'm going to go over here. And then I am going to draw the best I can for a straight line there. Well, at 60, we've got 2 years, or excuse me, days, beg pardon. I'll switch colors and we'll go blue. Well, 30, I'm going to read across. Okay. And on my X, I'm going to see where that is. On my Y there, well, it's about approximately 8.5 days. So my half-life is equal to the time when half of the amount decays. Well, from 60 to 30, that counts as half of that being gone. Well, now I can measure the difference here. Well, my half-life is 8.5 minus 2, so about approximately 8.5. So my half-life is going to be approximately 6.5 days. Sounds good, guys? All right. Now, this graph here is significantly less useful to us. We cannot find half-life off of this one. Now, why is that? I want you guys to look at the axis and I want you to think, why can't I get the half-life off of this? You guys got it? Hope so. So the answer is because notice here, this is half-lives. This is the number of half-lives. So after 1 half, well, 50% is going to be gone. We'll look at this. This is some variety of n, but it's percentage of original isotope remaining. So it's kind of a measure of n, but it's actually your n over NO is what this is, or that times 100. So it's kind of a measure of n, but not exactly. And we'll notice we've got 100% remaining and then 50% remaining after 1 half-life. Okay, that's great, but we can't get half-life off of this. So this is just showing the pattern that you would see. So it's nice to see the pattern, but you can't get any numbers off of it, unfortunately. But it's nice, though, you can really see that very, very nice, sharp exponential decay. So either way, whatever unit this happens to be, by the time we're after like 6 to 7 half-lives, there's like nothing left. Very, very little left. Alrighty-o. Ready for some calculations? Sure you are. Calculations are great. All right, so ladies and gentlemen, carbon-14 has a half-life of 5,730 years. All right, so there's the half-life in years. How much carbon-14 will remain? Okay, well, we've been asked for N in a sample after 17,190 years has gone past. So that is our time. If the original sample contained 15 grams of carbon-14. All right, so that's our original amount. So I'm not going to change any units here, ladies and gentlemen. Leave this in grams. You'll just get an answer in grams, and that's okay. Write your units with your final answer, and we're golden. Well, if we're trying to find N, well, we know N is equal to NO times 1/2 to the power of little n. Well, little n is the number of half-lives. Well, we have NO, but we don't have little n. Well, how can we find little n? Remember that little n is equal to T over TF. Well, guess what? We've got T, we've got TF. So we'll use this equation first, and then we'll use this equation second. Sounds good? Remember, this guy's not on your data sheet, so write it on your data sheet. If there was a diploma this year, then you would need to memorize that equation. I know. All the joys. So your first step, ladies and gentlemen, is we're going to calculate little n. I've already written my equation up here. So we have our total time of 17,190 years, and the half-life is 5,730 years. So in this case, we have had, once you divide this guy by this guy, you wind up with 3 half-lives having passed. Okay, so our second step, which I'll write up here for sake of space, is where I'm going to take this equation here to get n. Well, I've already written my equation here, so NO is our 15.6 grams, and times your 1/2 to the power of 3 half-lives. So plonk that into your calculator properly. Thank you. And once you do so, you get 1.95 grams. And that has our sig digs, and that has our units. Alrighty-o? Alrighty-o. So, next question. All right, radium-226 has a half-life of 1,600 years. So, all right, we've got T half is equal to 1,600 years. What percentage of a sample of radium will remain after 8,000 years? Okay, so while time is 8,000 years, and we have been asked for percent remaining. That's a wonky looking percent. Let's fix that. There. Okay. Well, ladies and gentlemen, let's look at our percent. Well, percent remaining is going to equal the N remaining, so the amount of radioactivity remaining, divided by the original amount times 100%. Well, you don't have enough information to get N and NO, but we do have enough information to get the value of N over NO. Okay. So with this one, that's going to be our final step. So in order to get this, you're going to have to use the equation N equals NO 1 to 1/2 N. Okay, well, good. So if I divide NO out on both sides, well, I get N over NO is going to be equal to 1/2 the power of N. Well, guess what? That's what we want. If we can get N over NO, we're good. We can get the percentage. Now, with this half to the power of N, so half to the power of a number of half-lives, well, we need that. But guess what? We've got the 2 times, so we're okay there. N is equal to your T over T half, and we've got those, so we're good. So we have to go in our order of 1, 2, 3. Sounds good? So our first step, ladies and gentlemen, let's get this number of half-lives calculated. So our time is, I dropped a 0 there, that should be 8,000. So 8,000 years, and we divide that by the half-life, and we are going to get the number of half-lives to be 5. So 5 half-lives have gone past in 8,000 years. And then for our second step, so 1/2 power of N. Well, I need to get this guy here. I can't get this or this, but I can get the ratio of N over NO. So by dividing both sides by NO, I wind up with 1/2 to the power of n. Well, I have n, which is 5. So now I can get the value of n over NO. So 1/2 to the power of 5 is going to give me, I just gotta scroll down a little bit here. Come on, computer. There we go. So once you put that in your calculator correctly, please, you're going to wind up with 0.03125. So that's the value of n over NO. Well, percentage, n over NO times 100. So I can get my 0.03125 times that by 100, because this value is equal to n over NO. So I substitute that number in there. And my percentage, once I've multiplied by 100, is 3.125%. So sig dix, for this one, I want 4 sig digs. Guess what? There's 4 sig digs. So, ladies and gentlemen, that is your percentage remaining. All right? Okay. So I hope you guys found that interesting. And I've got some practice problems down here at the bottom out of your workbooks. So have a look at those. And if you have any questions, sign up on Google Meet. You know where to find me. And have a good day. Enjoy this rainy Monday. No fires, injuries, or explosions. See you later. Bye.